And his superior was telling probably it has an orbital motion which is not uniform. Now we all know that usually planets are not very uniform, this kind of thing. So it was not. Only made this hypothesis. No, because light has it. So this is the bold hypothesis. He said sight is not instant, like Maxa said yesterday. What we are seeing today, and if it is coming from a far off distance, that was the picture some time back. And the farther the object, the light will come to us later. And accordingly, what we start seeing after 22 minutes, we measure the distance, time delay of about 22 minutes between these 2 points here. When one earth is there and the earth is there, we measure 22 minutes. And from that, going the orbit of sun distance, they calculated here an approximate value of 2.2 10 to the power 8. Right? Because light was so fast, there was no fast electronics available. Nothing is available. So you need to go to so-called large distances in order to measure this quantity. Straightforward. So they got this number, and at that time nobody paid much attention to this, that this number is so large. They knew it is fast, but very fast. And on 21st November 1676, these results were published in this journal. Right? Subsequently, so we are talking about 1676. Now, how does light propagate? We all know in space. But since 1650, very, very illustrious scientists have pondered over this question. Who are the people? Huygens, Isaac Newton, Thomas Young, Max, and Albert Einstein. You can see the kind of people who have worked in this area with their names, right? So, what was the picture? Christian Huygens gives his wave theory of light in 1678. And as we all know, waves propagating on this water surface, each wave has a wavelength, amplitude, and different waves have different wavelengths, all those things, speeds and amplitude. However, Newton was not convinced. Newton said that if sound, suppose there is sound which is wave, and I can hear the sound behind some, let's say, obstacle also. If there is an obstacle, I can hear sound, but I cannot see the light. So it can't be a wave. This was one thing. Then, sound does not cause shadows, light causes shadows. So again saying that it's particle-like, and then he believed that it is stream of particles, what he called as corpuscles. So his corpuscle theory was there. And also he believed that red photon is bigger than the blue photon. Newton believed red photon is bigger than the blue photon. Now, around this time when we are talking, one of the greatest inventions in science took place, which is electric battery. You will see why it was so important. And not that this Alessandro Volta was looking for a battery. He was trying to disprove his friend. Imagine, he was trying to disprove his friend. So what is the story like? Story goes like this. His friend is there who is Luigi Galvani. Luigi Galvani is a biologist. He experiments with dead frog. And he finds out that if you touch the legs of a dead frog with two different clips, one made up of zinc and another made up of copper, okay, the dead frog moves his leg. Okay, and this is what he called as animal electricity. Okay, he called this as animal electricity. All right, and he showed these results which he was doing for like 10 years or so. All right. Now, Volta thought that this sounds very, not so logical. It can't be dead animal electricity or this starts to show. And he realized that it could be simply because these two metals have slightly different potentials. So, either frog is merely a conductor. Okay, frog cannot be this, and it must be those two metals. And there were no instruments. So, how he started testing? He will take a coin made up of one metal, another coin made up of one metal, and put it on his tongue. Okay, and feel the kind of struggle. So you can try this, take a battery and take its positive electrode and negative electrode and tap on your tongue. You will see the kind of difference. By this method, he started optimizing, and finally he came out with what we call as voltaic pipe, which was basically nothing but a zinc plate and a copper plate, and in between an electrolyte material, either sodium hydroxide or this brine, right? So for the first time, the world saw a very reliable and a simple source of electric current. You can see how important it was. Okay, in a minute I'll show you. So steady flow of electric current for the first time, right? And this has played a huge role. Look at it. Using Volta's battery in just 1 year, electrolysis was discovered. Yesterday, Hemant sir showed electricity. Yeah? Water electricity was discovered. Humphrey Davy, that means Faraday's boss, he discovered 7 new elements. periodic table, 7 elements in just 1 year, 1807, 1808. All right. It was very simple. Take the solution, put the two electrodes. This one will come here, the other one will go there. Take them out and record a step. All right. 1820. Already a relationship between electricity and magnetism was established. That there is a relationship. 1820, Faraday produced even first electric motor also. So the mechanical, electrical energy was converted into mechanical energy. All right. Then he discovered transformer. He discovered electric motor, battery powered by this, and all the earlier atomic energy, this atomic structure experiments were also done using this. All right. So you can know that Volta's battery was absolutely essential requirement for our so-called technology-based civilization. Imagine if your battery of your phone is not working. What is the condition? It's like this is one thing, but I do not know what made him there. He put his thermometer here also, right, beyond red, infrared, and he found 1 degree higher temperature. Okay, we are not seeing anything there, but he puts his thermometer and he finds 1 degree. Now, 1 degree is not such a dramatic change. It is very easy to ignore this thing and say, okay, there is no change. No, he noticed it and went on further and finally showed that there is this region where there are waves which have heating capacity, and because they were below red, so they were called infrared. All right. He discovered this and published these results. He called them calorific rays, right? And these results were published in about 1800s. Now comes Ritter. This person says, how can nature be so selective that if I take an electromagnetic spectrum, below the red you have rays, and on this also there must be rays. Okay, this is the logic, right? He says, okay, how can it be so selective? So he started looking on the violet side, thinking that he will find infrared rays on the violet side also, without knowing that Herschel has already done these experiments, but has not put it into his paper because these were negative results. So he did the same thing and did not find anything. So then he was thinking something is wrong. That is where you come to know that if something is not working and if your logic is correct, you must change your measuring device. And what all he did was, he was good at photography, right? He was good at photography. He just took a paper which was soaked with silver chloride solution. Okay, silver chloride, as we all know, when you put it in the light, it goes down to black, it turns black, right? Because of the silver precipitation, right? So he did the same thing and now started putting here is the papers, right? So, and he found out that once he comes below the violet region, so-called ultraviolet now, these rays, again he finds an invisible rays there, right? And these rays have much more energy, much more capacity. They darken his silver chloride paper much faster compared to what UV and visible. So can you imagine just using a thermometer, somebody finds out a complete infrared region, and somebody using just a silver chloride paper finds out a complete ultraviolet region, right? And he called them chemical rays because these rays have the ability to induce chemical reactions in silver chloride. Now, in those days, how were the results published? This I mean, what's seen. So it was just a short note. This is in the German journal, okay? And what it says is, it's written in there, I will just translate it. Here says, on 22nd February, I also encountered rays alongside violet in the color spectrum of colors outside it by means of on silver. Silver chloride they call on silver. They reduce even more strongly than violet light itself. And the field of these rays is very wide. That means ultraviolet region is very wide. More to come later. That's how the entire discovery is published. Yeah. Around that time, another milestone experiment. I think this is one of the best known experiment and probably 11 people will know. I'm not sure whether in 10th they introduced, not yet, but 11th, 12th they come to this thing. The question was, is it wave or is it particle? That argument is still going on even after 100 years from now. And he thought, why not do one simple experiment? And what all he wanted to do was that I will have two holes in this aperture, and if it is particle in nature, I should see this result. This is what he was expecting, right? But what he found out was basically an interference pattern, right? Now, this was difficult to explain. How can you have this? All right. And what all he thought was, just thought that if you have one pinhole, let's say you have some string, and if you have one pinhole, some light is going on the other side, and you make another pinhole. So you can understand that light plus light is more. Light is easily understandable, not a problem. But you have light plus light leading to darkness. This is problem. How can you explain that? And this can only be explained if you have, all right. So light plus light is very convincing. You will have a little more light, two sources of light. But light plus light can lead to darkness. What does this mean? And this is where we get into this waveform here. And you can see if they are out of phase or if they are reinforcing each other, if they are cancelling each other. And accordingly, you can get this thing. And now he says, because light forms interference patterns, it must be a wave. All right. And this argument was so strong that for next 100 years, nobody talked about particle much. All right. For next 100 years, nobody talked about this. Right. And Newton's corpus of theory was practically abandoned till the quantum theory came into picture. All right. So if you see 1801, the information that you have is light or radiation is a wave, number one thing. And with the velocity will come to the little bit. Now the first velocity proper measurement was done by, I don't know how you pronounce it, I think it's a French name, Zoom, right? All right. So he used a tooth wheel which has 720 teeth in this. All right. It was a big one, and it was rotated by a motor. The motor was driven by the electric current, by the electric battery, discovered by Alexander Volta, right? And the motor made by none other than Faraday. So this was rotated, and the light is going through one of the tooth, and he has to rotate it so fast that when it comes back, it touches on the other one, and you can't see it on this. That was the speed. And now he knows how much is the distance. This experiment was done. You can see the apparatus here. So he takes a light which goes from one source, goes through L2, on the L3, mirror reflected back, and through this partially silvered mirror, it comes to this. And it will be blocked if it hits one of these tooth, right? That's how. And what is the velocity that he got? He measured a velocity of 3.13 10 to the power 8. Fairly accurate, right? And this uncertainty also comes because of the width of the tooth. There is a certain width of the tooth. So that uncertainty. This is about 4.3% higher than what we take as 3 into 10 to the power. Okay. One of his assistants, this gentleman, or whatever you call it, he changed, instead of the tooth, he used, because there you were thinking where it will block it. Whereas he changed this now to a mirror, and in that mirror, it has to just reflect. So both the points are stationary. The starting point and the after reflection is stationary. He can measure this distance and from rotation and other things. And he measured a velocity of 2.98. Okay, 1860. Right? Fairly accurate now. This is the value that was used by Maxwell. Okay, 2.98 into 10 to the power 8 meters per second is the velocity known with this accuracy in 1860. Comes in Maxwell, right? So you will see over time how it has gone. Galileo said extraordinarily fast, you can't do anything. Romer said, 2.2 10 to the power 8. Then Bradley from aberration of light was also very accurate, but these rules are not very often quoted in the literature. 3.04, tooth wheel 3.13, Popper gave 2.98, Michelson interferometer for the first time gave 2.99. And subsequently we have been improving from 0.2% all the way up to now. You can see how many zeros are there. This is the accuracy. So now we know till a fraction of a meter. So you have this 458.6. Okay, this is the accuracy of velocity of light. Okay. And that's how it is a fundamental concept. Now comes Faraday and Maxwell and immortality. I think these two were made for something like that. Okay. Michael Faraday, an FRS, chemist and physicist. People say if Michael Faraday was in this century, 20th century, he would have got 6 Nobel Prizes. Okay, because he discovered benzene, he discovered electromagnetism, and whatnot. Okay. And about 40 years junior to him, James Clerk Maxwell, Scottish physicist and mathematician. Okay. They two were there. And if you see Michael Faraday, for chemistry and physics, he was one man army. Okay. You can take any experiment, he will do himself. He doesn't rely on anybody else. He will think, he will do his own experiments and so on and so forth. He figured out how he can generate electricity by moving magnets. Alright. This was the principle behind electricity generators, the principle of induction, first motor, 1831, so on and so forth. Several things. Now, this is what says how a lecture can change your life. So once, when Maxwell was visiting London, where Faraday was there, he went to listen to the lecture, which he was giving to Faraday, the Royal Society. And he found out that Michael Faraday is correctly describing what changes. So Faraday had described his effects very clearly in words, but he was not educated enough to put it into mathematical equations. He was never trained as a mathematician. Okay, Maxwell listened to that and he thought, I am a mathematician, I can write this. So he wrote that equation and finally found that the solution of this equation is basically wave traveling at a particular speed. And what is that speed? You put in all the values here. Okay, so you have mu 0, you have this epsilon 0, and these values in vacuum are known for this. So these are the definitions here. E0 and all these values are known. And once you substitute it, C is equal to this, under root and all these things. And what he gets 3 into 10 to the power 8. What is the best well-known value at that time? 2.98. Alright. So he just sees it that these two numbers are so close and it just can't be a coincidence. Alright. Again, in 1862, this is the value known and what he gets is 3. So he again made a very bold hypothesis. Okay, people did not believe him that time. Once again, it seems we have a strong reason to conclude that light itself, including the radiant heat, that the infrared one and the UV one, okay, is an electromagnetic disturbance in the form of waves propagated in the transformer according to electromagnetic laws. Okay, but somebody has to prove it. Okay, he has given a theory, his velocity matches, somebody has to prove it, right? Okay, this is done, so you can see it's a transverse wave. Now, we normally think that Maxwell gave 4 equations. That's not correct. Maxwell published this paper, which is a long paper of something like 53 pages. Okay, 53 pages, long paper, right? In which he had 20 equations. 20 equations. We think it's 4 and not 4 really. And so Maxwell died because of a abdominal cancer, and it was the same disease which killed his mother at around the same age. Okay, around 48 only. And he could not see his theory being verified that this is an electromagnetic. He died. He gave a theory and died. This gentleman, Oliver Heaviside, was the one who applied vector algebra to his equations and finally came out with 4 equations which are nowadays used. So it was this person, but you will not find his name being mentioned anywhere in the literature. All right. This, once you do science, it is very, very important that you keep track with the technology, what is happening in other fields, and how new instruments, new developments, either more sensitive or altogether different. Now, this is the time in 1857 when they improved the vacuum pump, and vacuum pumps could go to about 10 to the power minus 3 for the first time. So this gentleman, Heinrich Geissler, basically a German glassblower and a scientist, he made this tube, started removing the gases, and he saw on this right side, you see where the anode is there was a green glow on the glass. And he was wondering what is this. When he reduces the pressure, suddenly he starts seeing a green glow on this. Alright, they have applied a high voltage, and that high voltage is being fed by Alexander Volta, the voltaic coil. Alright, all these things. You see how they are very nicely connected. Comes Johannes Otter. He thought, let me see what are these. So introduced a solid object just before this green emission where he is seen. And he sees that you can see a shadow. Alright. And then, so he suggests there is some kind of beam, rays or there. Finally comes Brooks. Okay, he did like this and he put a cross in between. And he could see the image of the cross on the backside. Alright, from here. And the question was, are these rays, I mean something like a wave, or are they particles? Charged particles, basically. That was the question being asked. Eugene Goldstein, he placed a paddle wheel, you see, and he found that the paddle wheel starts rotating. So they have so much energy that the paddle wheel is rotating. Alright? And he confirmed that they are negatively charged, and he named them so-called cathode rays, emitted from cathode and they travel towards all these things. Around the same time, Suddenly, in between, this gentleman, Heinrich Hertz, who was mentored by none other than Alberts and Kirchhoff. I mean, you must have heard his name, Kirchhoff law and several other things. Okay. They gave him one fellowship and asked him to confirm whether Maxwell's theory is correct or not. And he was thinking, okay, he'll start working, and he was doing dilly-dallying, and he was not really working. But one accidental experiment one day, he was to demonstrate one discharge, a high voltage discharge, he was to demonstrate to his students. So while he was preparing his lecture and he was trying to demonstrate, he noticed that he's creating discharge here, and 5 meters away, there is an identical loop where he's creating. So there is this two balls are there, among which high voltage will create a spark. And about 5 meters away, there is another similar loop line. And when he discharges here, a discharge appears there also. Okay, so these two are not connected. They are not connected, but he sees the spark there also. And he immediately remembered Maxwell's theory. So this is how it goes. Okay, you have this discharge here, and the S is the source, and this is the receiver. Okay, whenever he creates a spark here, it goes there. And he could see this is electromagnetic wave traveling here. And it will travel so fast, you can't make it that fast. And seeing this, then he started doing all these transfers and the properties of the waves he found out. And he confirmed whatever Maxwell said, everything was true, right? He used these waves to until radio waves. So these were for the first time radio waves carrying high current, causing spark. All right. In addition to that, he also discovered what is called as photoelectric effect. Okay, photoelectric effect was because of Heinrich Hertz. And this gentleman called Philip Lenard, he was his assistant. All right, he was the one who was doing experiment. All right, but again, Heinrich Hertz again died quite early, just at the 36 years of his age, brain tumor. Okay. Philip Lenard, this is Philip Lenard. He's the one whose data Einstein used to validate his photoelectric effect explanation. Philip Lenard. From 1899 to 1902, he collected this data, all the data, and published it. Again, about a 40-page paper. All right. That data was processed by Einstein for 3 years to come up with explanation of photoelectric effect. Again, now assuming particle nature of radiation. All right. What he did was, it was very significant. People were talking about cathode rays. And any change you wanted to do in an experiment, so you have a full tube which is evacuated and you are saying something and you want to change some parameter. When you want to change some parameter, you have to destroy that vacuum. Again, go make some change. So he thought, can I bring this cathode rays outside? Can I somehow bring these cathode rays outside so that I can do experiment outside? And he cleverly put what is called a 26 micron thin aluminum window, okay, at the outside, at the outlet. This allowed the cathode rays to come out about 2.5 centimeter in length. Okay, so you have now cathode rays here traveling in air, something like 2.5 centimeter. And whatever changes you want to do, probably you can see something else. This is what was called Lenard tube. Philip Lenard got Nobel Prize in Physics in 1905 for his discovery, work on cathode rays, Lenard tube, and photoelectric, and so on and so on. Now comes the most important point, discovery of X-rays. It was on 8th November 1895. William Conrad Röntgen in his lab. The place is Würzburg. It's a Friday. Okay, he's doing experiments and he was using a Lenard tube. And what all he does is, you will see on the top it's written parameters. Okay, why it is written parameters? An experimentalist must try to change his parameters and see what happens. The only thing that he did on that day, typically people were applying something like 25 to 30 kV. He increased the voltage much more than what people were applying on that day, right? And to his good luck, there was a phosphor, barium platinocyanide, which was lying on that in his lab. And he suddenly realized that this phosphor starts glowing emitting light. And he was wondering that what is this light coming into? He thought probably these cathode rays are going and hitting because there is a high voltage. So now he has to change the tube if he wants to make sure that it is not because of this Lenard tube. So what he did was he went back to what is Cook's tube. In this case, there is no aluminum window. All right. He brought this, and so that no light is emitting out, he covered it with complete black paper, very thick black paper. So nothing should escape from here, and he still wanted to see. And the results were still the same. No matter how deeply you cover, that barium platinocyanide was still glowing. And this time he realized that something is happening. Okay. Also, he noticed that whenever he was crossing this region, he was able to see some sort of a skeleton on this. Okay, which was very surprising to him for the first time. Yeah. So suppose this is this image and I am crossing this, you can see some sort of my skeleton being seen. We will come to this in a minute. Yeah. So this is what was done, and then late afternoon. Now here you will realize if you have a new result, you should be fully focused on that. I must tell you here that several people he had seen X-rays before that, but they never paid attention on this. And some of the one person who particularly saw X-rays, he thought, okay, I'm going for 3 weeks outside, some holidays and all this thing. I'll come back and publish my results. Before that, Ranjan has finished it. All right. And all of you know, 1901 Nobel Prize was given. So for the next 3 weeks, he literally slept in his lab. His wife used to bring food for him in the lab. He was not leaving his lab. 3 weeks, Ranjan was in his lab continuously from there. Okay. All right. Notice different repeated experiments. Ate and slept in laboratory for 3 weeks as he investigated properties of X-ray. And he called them X-rays because he was also a mathematician, so the unknown is equal to X. Okay. So X-rays, and then that's how it started. The name started. So who was the first the first X-rays taken? That was of his wife's hand. Okay. I'm sure no scientist will dare to take his wife and do experiments on her hand. But this is Anna Bertha, his wife. First medical X-ray was taken on 22nd December 1895. All right. And this was the X-ray. You can see her ring also on this. All right. First finger. And when Anna Bertha saw this photograph, she exclaimed. She said, "Here, I have seen my death." This is how she reacted to what she saw. Okay. Now this method became so powerful, as I was telling, that doctors realized immediately its importance. They can see in the body, or they can see the body without really opening it. Before that, if they had to see something, they have to cut open and find out what is inside. Now they could see without that. All right. And this appeared in what is called as Reports of the Meeting of Physics and Medical Society of Würzburg. Okay, Würzburg is a place in Germany. There it appeared. Right? When it appeared on 28th December 1895. 28th December 1895, it appeared in that report. And on 5th January, this news was carried in the Austrian newspaper. All right? It appeared in the Austrian newspaper. When it appeared in the Austrian newspaper, on 20th January, Henry Poincaré, French Academy president at that time, he read out Ranjan's paper. There are X-rays and so much. The Europe is going in all ooh la la more kind of a thing that they have discovered something. Ranjan's paper he read out, and there Becquerel is sitting. Henry Becquerel is sitting, and Henry Becquerel has some phosphorescent materials. Okay, so he thought if X-rays produce phosphorescence, can phosphorescent materials on being supplied energy produce X-rays? This was his logic. Okay, that logic, but in principle true. So what he thought was he has some uranium compounds which were given to him by his grandfather. Okay, let me test those. He took all those uranium compounds and put them in the sunlight. All right, put them in the sunlight without realizing that they have uranium. All right. So he kept it in the sunlight, and in the evening when he had put his films, X-rays, and all these things together, he found out that he is seeing similar rays what Ranjan has seen. And Ranjan is using 50 kilovolts energy, and I'm not using even energy. I'm just using sunlight. Okay. So he thought, very fine, I can also produce X-rays without even supplying energy. Now comes very strange things. So he started his experiments in February 1896. Experiments began, and his first result was on 24th February 1896. And all Mondays, every Monday, there used to be this French Academy of Sciences meeting. And in the very first meeting after his results, he shot to them and said, I have also produced X-rays like Ranjan without even high voltage. And now people were shocked. How can you do that? All right. But then he was going very systematically. So one day on this, you can see this cross and all this. On 26th and 27th February 1896, it was partly cloudy. So he thought now because there was sunlight, so if I now there should be less energy absorbed by phosphorescent material, and since less energy has been absorbed, there should be less SLAs, and my images should not be that sharp also. But he was really surprised when he developed those films that the photographs were still equally sharp. And now you're surprised that if there was sunlight for only maybe, let's say, 2 hours or 1 hour, how can it be sharp? He did a blank experiment, not to expose anything, and he still found it equally sharp. And then he realized it has nothing to do with sunlight. All right. So you can see how quickly he could do these things, and he immediately changes this thing. 26, Gallup film still sharp. Immediately on 2nd March. Earlier one on 24th February. Okay, he says that I'm producing X-rays similar to this thing. On 2nd March itself, he has changed his results. And now he says that he's not supplying any energy. I have uranic compounds, and from there, invisible rays are coming. Okay, this was very strange because if you talk of 50 kilovolt being applied and certain portion of it gets converted into X-rays, it's not very surprising. But when you talk that out of nothing, then I'm getting high energy rays, that is very surprising. Okay, that's how it was there. And accordingly, these were called either uranic rays or vacuum rays. Okay, people did not call them X-rays till now. Now, this is 1896. So 1896, something has been discovered, what is called now vacuum ray. Okay. 1897 is again a very important year. This is J.J. Thomson. He wanted to do engineering. His father died. Funds were not available, and accordingly he changed over to mathematics. He was a wrangler working this, and he started working at the Lord Rayleigh. Started working with Lord Rayleigh, and subsequently this position became vacant in 1884. So several people applied for that, but the youngest of them, Thomson, was selected, and who was a theoretician, and the position was for an experimental research. So people were very surprised why he has been selected, who is so young, who is not in the field. However, for whatever reasons he was selected, and this was for an experimental position. So Thomson had to quickly choose a field, experimental, where he will produce these results. And at that time, the hot research area was transmission of electricity through gases. Everybody was working on that. So he also chose that. But the problem was Thomson was very, he was very bad with experimental skills. So his assistant used to be very, very careful that he should not spoil anything. He will end up spoiling some of the other instruments. So his name was Everett. Okay. Thomson was very clumsy. He's good as a theoretician, okay, but not an experiment. Everett designed all these whatever this E by M experiments you say, these were all experiments and it was designed by magnetic field. We use this apparatus for E by M, and yesterday you heard the story of electron charge and all those things. And finally, in 1906, he gets a Nobel Prize. So 1896 we have these uranic rays. 1897 we have 1895 X-rays being produced. 1896 uranic rays. 1897 electron. 1898. Maria Curie. Okay, Marie Curie, a very gifted child. She knew about, I think, 7 or 8 languages. She could speak very well. Okay, she was a bit of her mother died when she was young. Her sister died. All right, they did not have money. Her father was fired from a school job because the Russians took over their land. All right. Finally, she worked as a mistress in some houses and supported. Look at this. She traveled from Poland to Paris, which is a journey of something like 1587 kilometers. Okay, 1600 kilometers. Imagine the train speed in those days, 1896 or so. You can imagine. So it was a 4-day long journey, and she bought a ticket, what was called as 4th class. This class doesn't exist now. 4th class ticket, in which you will carry your stool, you will have your some sort of a sleeping arrangement, and your water and everything. And 4 days like that she traveled. Stayed in cheapest available rooms, married Pierre on 26 July 1895, worked in labs which are dampened on these things. All right. In 1895, as we know, X-rays were discovered by Röntgen and subsequently uranic rays. Marie Curie wanted to work on X-rays for her thesis. All right. However, Pierre advised her, no, that is not fascinating. You should work on this uranium rays, because if you take some substance and apply very high voltage, part of it gets into heat. That's something very surprising, right? However, this uranic rays without anything, you have nothing, and you are getting high energy rays. How is it possible? Okay, radioactivity is not known till that time. So her advisor was Gabriel Lippmann. And what she thought was that there were 2 ways. So this is where the idea comes that when you want to quantify something, there were 2 ways. You take these uranic rays, they are very thickness, and they will go through a metal pocket or anything and darken the photographic film. This was one way. But there is no quantification in that. Okay, and this method is slow. You keep it overnight and next day you will get it. Marie Curie wanted a fast method, and that fast method was provided by Pierre Curie. What Pierre Curie had discovered? He had discovered a piezoelectric detector. Okay, so this piezoelectric detector, when you take this thing, put a pressure on that, and it creates an electric charges. And if these electric charges can match the electric charges produced by the radioactivity, and you find a null point, then you know how much charges are being produced from the radioactive source. This is what she did. So she wanted to quantify, and that's where the importance of quantification lies. That you have a method to quickly know what it is doing. Okay, method. So she discovered these, and because she was not getting some reproducible results, she complained to me, "What is this method you have discovered? I'm not getting reproducible." It was that the method was devised for a source which had sufficient, give sufficient charges. In her case, the charges were not sufficient, radioactivity. Okay, so he made it 20 times more sensitive. Okay, accordingly, and trained her how to measure those numbers. This is her lab apparatus. So you can see this central one, which you see here. Okay, this is the one on which they were putting pressure. All right, these are the chambers, different chambers in which the material was kept. And this material, because of the high energy relations, will cause ionization, and that ionization will create ion pairs. You will have electron and ions, and this is what will create the pattern. And these charges need to be matched by piezoelectric crystal in order to know what is the total number of charges. Now, 16 December 1897, they started their work. Mary was working on this, and because these results were so strange, on 5th February 1898, Pierre also joined her. Okay, let me understand what is happening. He was also a physicist. And on 12th April, they read out a paper to French Academy on the possible existence of a new element. In those days, how the new elements were verified? New elements were verified, you take a material and purify it many times, 10, 20 times, and then record a spectrum. All the lines that you see in the spectrum should not match with any existing element. Then you have a new element. But in radioactivity, you did not have that much material to do these things. So Marie Curie came out with this idea, okay, henceforth, you will not be doing this, we will be using the emission of energies, which comes out of X-rays, all right? And on 14th April, they further did this with chemist Gustav. By mid-July, they were very sure that they have a material here, okay? And activity of compounds depended on this, radiation outcome, and Curie finally found out polonium, which was 400 times more active. And how they found out? They realized that if I have only 1 gram of uranium, okay, so this much radiation, right? I'm finding 400 times more, and now I'm doing quantification. Otherwise, film method, you see more or less similar results. They were convinced, and accordingly, on 18th July 1898, they published this paper announcing a new element, and she named it polonium. Why? Because she wanted that Russians had wiped out Poland. That means no Poland was existing at that time. Marie Curie said, I'll put it on periodic table, and nobody can wipe it out from there. Okay, and Pierre had no trouble with that. Okay, he doesn't want to call it Frenchium or something like that. Name whatever you want. So she said, once I put it on periodic table, nobody will ever remove it. So till we know periodic table, polonium will remain there. All right, that was honored. It was a landmark paper because for the first time she used a word called radioactivity. Before that, radioactivity was not used. All right, and they thought that this is the most significant discovery. They have found a new element. All right, without realizing that after 5 months they had another element. 26 December 1898. So you can see 2 new elements being discovered in 1 year, and all together by same method. All right. So they discovered, published these papers, and instantly they were very famous. All right. At one time, radium was so famous that people wanted to use radium lipsticks, radium shiners, radium like this, because they were not knowing that there are harmful effects. Okay. She was called, she invited to places where she can give talk on this. Now comes the so-called Nobel Prize conspiracy. Okay. This is an important issue. In 1901 and 1902, Marie Curie and Pierre Curie, they were recommended for the Nobel Prize. Alright. As we know that 1901 went to Ranjan and 1902 went to Lawrence. Right? These were there. And in 1903, somehow Becquerel got himself and Pierre Curie nominated, and they left Marie Curie behind. Marie Curie's name was not there among this nomination. And nomination was done by Gabriel Lippmann, who was her PhD supervisor, Marie Curie's PhD supervisor. This news was unofficially declared by this gentleman called Magnus Leffler, who was a mathematician. He discovered in private to Pierre Curie. Pierre Curie was so outraged, he said that if it is without Marie Curie, I will not accept even a Nobel Prize. So she has to be there. She was the one who discovered this. Now they realized there is a problem. So they discussed in the committee. And then subsequently, this gentleman called Bouchard, who was there. Okay. Bouchard was Alfred Nobel's personal physician, who had the rights that he could nominate anybody anytime except himself. He could not nominate himself, okay? But he can nominate at any time anybody. So he was asked, then he nominated her, and the prizes were announced on 8th October 1903. Curie and Becquerel got 50%, Curie got 50%, and he got 50%. And obviously Becquerel for discovery, he was the first person to say that discovered, and Pierre Curie for the subsequent one. Alright. And on 10th December, when King Oscar awarded the prizes, it was given only to Becquerel because Marie Curie was not well, and Pierre did not go to receive Nobel Prize, leaving his wife behind. Can you imagine? He did not go to take Nobel Prize just because Mary was ill and wanted to be ill. Okay, that kind of a thing. But here comes a very important point. Luckily, in that nomination and everywhere, nowhere there was mention of polonium or radium. They only said for discovery of radioactivity and work related to it. They did not mention polonium. And this is what gave rise to her second Nobel Prize. Otherwise, she wouldn't have got. If this was mentioned in there, she did not get second Nobel Prize. Okay, this paved the way for her. Now you will see what was Marie Curie at that time. This is first Solvay Conference, 1911. And the title was Theory of Radiation and Quanta. And you see this picture. I think you will very rarely see a picture more intelligent than this. You will read out the name. Okay, Planck, Sommerfeld, de Broglie, Wien, this, Einstein, Langevin, Rutherford, Poincare, Curie, Perrin, Lawrence. How many people are there? All right. Only one woman, Marie Curie, in the sitting, second from right. All right. And out of 24 people which you see, 10 were already Nobel laureate or they will become Nobel laureates also. Okay. This is the power of this. And Marie Curie only one. Now, people often think what was so great about Marie Curie that she succeeded and not other French people. They were also there. They were also doing work. What was so great about Marie Curie? Because she was an obsessed researcher. Okay. What do you mean by an obsessed researcher? Or if I say he's an obsessed researcher, what does it mean? So look at here. Marie Curie inspired many women. 1920 women applied to her that we will work with you without any such. Okay. And one of was none other than Lise Meitner. All right. We come to that. This picture has been taken in April 1921. At this time, she was 54 years old. She has already won 2 Nobel Prizes. She is director of that institute. So you are director of an institute, you have 2 Nobel Prizes, okay, your daughters, everything is there. I mean, will you work in the lab? But this is Marie Curie. Wearing her lab coat, she will be still in the lab. And that is what you call as an obsessed research. She had to separate something, verify her own results, verify her curiosity, doubts, whatever you say. So she has to do this. But as I told you, one of such volunteers was Lise Meitner. She applied to her. All right. She was about 11 years here. And she was rejected because she was found to be too bright. Lise Meitner was too bright to be accepted because that position was reserved for Irene Curie. Otherwise, Lise Meitner may not allow her to go. Comes in Ernst Rutherford. This is another man, the nucleus man. About Ernst Rutherford, you will see, he was one person who was always thinking about nucleus, and nucleus. He was only thinking about nucleus. This was the okay. He joined. He came back from this New Zealand. Joined J.J. Thomson, as he's called JJT, worked on cathode rays, X-rays, and finally radioactivity once again. And after 2 years of joining, he did not have a job in UK, and as a result, he could not stay. And he was offered a position in Canada, so he moved to Canada. Next 7-8 years, he worked in Canada there, and all his important work about radioactivity came from here. And he dedicated his complete life to understanding radioactivity. He was so much deep into radioactivity. Every 5 years or 10 years, he was writing books in which 50% of the work was coming from his own lab. You are writing a book, and 50% of the work in that book comes from your own work, which was done in the lab. All right. The great thing about Rutherford was he will do what is called as Vidyankan experiment. So when I say Vidyankan experiment, it basically means that you are doing experiment right in your head, and then you know, okay, if this is the result, this is the explanation, and if this is the result, this is the explanation. Okay? And accordingly, even before the experimental results are available to him, he has already done everything in the mind. For example, take this thing. When people saw that uranium is emitting some radiations, okay, so he did this simple experiment in which he took a uranium salt, covered it with some aluminum sheets, which were like some 5 micron thick. All right, he found that initially there was a linear decrease, then there is no decrease subsequently, and he said, okay, this contains of 2 types of thing, one alpha particle and another beta particle, and one is stopped immediately, which is a high energy, and other is stopped later on, like this. We have done this experiment. Okay, and mixture of 2, beta alpha. He was the first person to give concept of half-life. Okay, concept of half-life was first time given by him only. So he found out irrespective of what salt you take, it is directly dependent on that radioactive element. In this case, uranium, on the amount of uranium that you have. Concept like this, and he also discovered gamma rays and all this nomenclature. Rutherford Geiger counter gold foil experiment, we all know, is from this. Now, here it is one very important thing to tell. People say that he was the one who participated in that. But you will see, if you look at it, in that paper, Rutherford's name is not there. Though he asked them to do this, the gold foil experiment, those experiments were done, his results were published, but in that paper, Rutherford's name is not there. Okay, it is only these 2 people. All right, model of nucleus, the first successful alchemist. All right. Now he was in Canada and he was feeling very uncomfortable that most of the research is going into Europe. He wanted to come. All right, but he was not getting a chance. As luck would have it, there was somebody called Sir Arthur Schuster. He had a chair in physics, University of Manchester. He inherited a fortune. His father-in-law, somebody died, and he inherited a fortune. And he said, I will vacate this position only on one condition, that only Rutherford is to be selected. Okay, so no announcement, no advertisement, nothing. Only Rutherford will be selected to this position. And Rutherford came back to Manchester, right? Cambridge and Manchester. And this experiment tells how genius he was. He took a radioactive source, which was emitting alpha particles, allowed them to go through a window, and they wanted to know what is this alpha particle. Okay, he allowed this to go into the air and put them with an electrode. And as he sparked those electrodes, he could see helium spectrum. Okay, and then he immediately realized that alpha particles are nothing but a helium. So this, I mean, he used to do very, very simple experiments. Now, this is an important thing. He says transformation at Manchester. Rutherford used to say that all science is physics and everything else is stamp collecting. Okay, so he considers science only as physics and everything else is stamp collecting. And you see this, all right? And in his Nobel speech, he mentioned there, for his, he got a Nobel Prize in chemistry, though he did work in physics, but he was given Nobel Prize. Now he cannot say no to the Nobel Prize also, all right? And he cannot say that he's wrong also. So he said during his Nobel Award speech, he said, I had dealt with many different transformations with various period of time, but the quickest I met is my own transformation in one moment from a physicist to a chemist. He always considered himself as a physicist, that physics is the only branch, but one overnight, the Nobel Committee turned him from a physicist to a chemist. Now comes neutron discovery. Now, neutron discovery is a fascinating thing. people think that Chadwick was really searching for neutron. He was searching, but he was not getting an idea. And that time there were two disturbing nuclear effects, what they call disturbing nuclear effects. One was that people knew that the atomic number is, let's take nitrogen. So atomic number is 7, but atomic mass is 14. And only because proton and electron are known, so how do you say that mass is 14 if there are only 7? So somehow it was believed that in the nucleus you have other things, you have another 7 protons which are associated with electrons. So there was something called nuclear electron theory. That means the electrons are there in the nucleus along with protons, and because they neutralize, so you will not see their charge. However, because they are present, so their mass has to be taken into account. And it was Rutherford who was always asking Chadwick, look for these neutrons, look for these neutrons. And Chadwick was trying. For 10 years, he was trying and he did not get any evidence. Now came an experiment. Okay, Bohr also tried his experiment in this, and accordingly, a strange result was obtained in Berlin, in Germany. So this experiment was done by Hans Bethe and Becker. And what they found out was, when you do this reaction, alpha plus this particle, they found out that they are getting a very high energy radiation, which was able to penetrate three times the lead shield which they had already used. That means if you have seen all the other nuclear reactions, so it was being stopped, let us say, by 1 feet. Now this new nuclear radiation was not stopping even with 3 feet of radiation. And accordingly, in order to cross these 3 feet, they found out that this radiation has to have an energy of something like 50 million electron volt MeV, which is a very large amount. So this was somehow not convincing. Okay, they all assume that you have a lighter nuclei. Okay, an alpha particle comes, mixes into that, forms a compound nucleus, and that compound nucleus gives rise to an energetic number, right? But that was not true. So Irene Curie also did similar experiment, and Irene Curie had no idea that neutron should be existing. So that is why I say that you should be very much aware of what are the current discussion going on in your group, what is the current literature. You should be very, very careful about that. She had no idea, otherwise she was seeing this neutron. Alright. Subsequently, James Chadwick, he attended this conference, okay, and went to Rutherford, and he told Rutherford, okay, these are the results. And Rutherford immediately said, this is your neutron. Okay, this is your neutron, this is not gamma particle, high energy particle. So if the assumption is that you take 9 beryllium and mix it with alpha and you get 13 carbon gamma, that's not correct. You should rewrite it as this, 9 this plus 12 carbon and a neutron. Okay, so first establish whether you are getting 12 or so, alright, and 1 neutron. So Chadwick's work was now boiled down to only verifying that it's a neutral particle and a neutron and not a high energy gamma. That's the only thing he did. And this he finished in 2 months, and accordingly he published this paper on a possible 1 month later, just 1 month later, and he got Nobel Prize in Physics for 1935. Okay. Subsequently, Joliot Curie discovered this artificial radioactivity, and they were given Nobel Prize in 1935. So you see, whatever results they had, for which in 1935 Chadwick is getting Nobel Prize, was actually their own result. But because they did not have this idea of neutron, they missed it. Okay. This is the one here. Okay. Picture taken at that time. Another, they were the first one to see fission. All right. They missed even this also, and subsequently Otto Hahn and other people, they discovered. Lise Meitner gave the experimental results and all these things. Okay. Now, I normally say, if you want to do science, how one should go about it. So these are some quotations. You really don't understand something unless you can make a model of it. If you are doing a science, you should have a mental picture of what you are doing. Otherwise, you are not doing science. And you only know something if you can measure what you are speaking and you can express it in numbers. Okay? You should always be able to express that in numbers if you are measuring something. And that is where the power of quantification lies. Alright? And if you cannot measure it, then it's not science. This is law of calculus. If you cannot measure it, then you are not doing science. You are just little more aware than a normal person. Okay, I know this and all. But the most beautiful quote is this by Enrico Fermi. What Enrico Fermi says is, if the experimental result confirms hypothesis, then you have just made one more measurement. That means, okay, something is predicted and you make measurement and it is in line with this, not a problem. But if your results are contrary to the hypothesis, then you have made a discovery. right? So, in summary, I wish to tell you, science has evolved due to curiosity, hard work, and persistence. Okay, so it's just beyond knowledge. Okay, curiosity, and I know something. No, more than that. All right. Set up an experiment which can answer as many questions as you want. Okay, just don't do only this and ignore all of the results. If you are getting some result which is not fitting into your destiny, record that also. Think of an expression, talk to people, discuss, ponder over it, and whatever. Do not be biased by opinion. Okay, many times you are biased. नहीं, ऐसा होना चाहिए. We force our results. We only show those results which are in that direction, not otherwise. Neither your personal opinion nor even if somebody great is telling you it should go this way. No, don't get biased. Whenever there is a possibility, try to measure it, quantify it, go to the best sensitive method which can tell you whether it is 1% or less than percent. All right. Reproducible results, okay, but unexpected. These are unexpected results, but they are reproducible. Okay, pay attention. Something something significant is hidden there, and science never shy away from making bold hypotheses. Okay, Romer made bold hypothesis, Marie Curie made bold hypothesis, even Henry Becquerel made bold hypothesis. Okay, you are saying something very unusual. Okay, be up to date with the published results in your field. All right. And I would like to acknowledge Jyoti sir for his kind invitation, Professor Vaya for making part of this program, Dr. Mohanty, who is our Secretary, DE and Chairman AEC. I also had the pleasure of discussing these results with Thakurkar sir, Vyas sir, and all these things. And thank you for your kind attention. Philosopher Simon Will said, attention is the rarest and purest form of generosity. Yeah, I'll be happy. I'll be happy to answer any queries you might have.
Yes, students. So let's see, can you maintain the same zeal which you showed on the day one? So any questions?
Any question related to this? Or, even I can answer for GA also. Yeah. She wants a mic.
Good morning, sir. In that slide, there was written glass girl, and what does that mean?
Okay. Before we started getting these fancy instruments, okay, initially when an instrument is made, you don't have it ready-made in the market. Okay, so you design something. For example, if I want to test something, even a simple vacuum chamber. Let's say I want to make a vacuum chamber. Stainless steel, rubber O-rings and all things came very fine. What people initially did, they simply had a glass blower, just suck a vacuum out of it and seal it. Okay, that is a tube. And inside you can have any material which can lie in vacuum for a long time. So a glass blower makes your design the way it will be simply out of heating the glass and blowing it. Okay, so you have a glass tube, beaker, whatever. And so you can see Thomson's entire experiment is out of a glass only. He just puts into electrodes, which are electrical electrodes, plus minus, and similarly to magnets, okay, north and south, and diverts the heat. So initially everything, at least even when I joined BRC, we were given 15 days training on glass blowing. So you can make something of your own to try out. Okay, this is an important training in the life of a scientist, because something you want to make and test, that instrument doesn't exist. So you start from your own. Even simple putting electrodes into that.
Good morning, sir. So can you please explain the concept of half-life?
Half-life says this thing. Suppose I take uranium. Okay, every substance which is radioactive, is continuously emitting some sort of particle. Let it be alpha, beta, or gamma. Alpha is the helium nucleus. So it starts from here. Suppose I say I took 1 gram. All right, I took 1 gram. So what is the time in which this 1 gram will become half a gram? So if I'm measuring uranium, okay, and I do some chemical test or some other test, so for 1 gram I'll get, let us say, X amount of signal. Now what is the time in which this signal becomes half of it? So that is the half-life. Okay, and this is so element specific that by using half-life you can say this is uranium, this is plutonium, this is what, this is what. In fact, you'll be surprised to know that different isotopes have different life. For example, uranium-235 has a different half-life compared to uranium-238. Okay, and this is the reason that in nature you are left with now only 0.7% of uranium in the form of 235 and 99.3% as 238 because of their different half-life. Yes, it is signature of every element. Its signature. So if you have a given half-life, it is very, very characteristic of this. You might have two elements which are nearby. Check for that. So what they emit, so it's alpha, beta, or this thing, and what is their half-life determines what is that element. Yeah. Somebody wants to ask there.
Good morning, sir.
Hmm.
So my question is: are there any possible ways to are there any possible ways to control all the harmful ways of radiations and make it harmless for everyone?
Difficult question. The question is that what do you call as harmful? So normally everybody maybe in this or everybody else thinks that nuclear radiations are harmful. They are strictly not. They are used even for cancer treatment. Right in Bhubaneswar, right in Jatni, we have this Tata Memorial Center Hospital. Okay, one there. All right. You will see. So it's just a question. I'll put it like this way: driving car is harmful or harmless. All right. So if you drive at excessive speed, not taking care of others, then it is harmful. But if I can control it, and if I have control over the parameters on this thing, so radiations are as such, but beyond a certain limit, you might run into problem, and that is where you need to take proper precautions. You need to have shielding and whatever it is. I have been working in nuclear institution for 40 years. Okay, never ever a problem. So once you are doing these things, you have to have a proper care. Do not get exposed to excessive radiations. That's right.
Yes.
Can you also talk about some of the cutting research in this field which is happening in India? Because most of the earlier references are from Europe and other countries, right? So,
You mean the radioactivity or?
yeah, all like say radioactivity, uranium, all of this.
See, this is a very general question. I also keep wondering that what was so great in Europe that we did not do. So there are many factors, all right. But one thing earlier, that we had lack of instruments. We did not have our own instruments, and that is where Raman's role become very critical. Raman always said that it has to be an idea-based research. We will not have all the instruments. So technology, other things, everything came, and group of discussions. Okay, so Europe had a very thriving society which discussed, which met, which published. All right, we were far behind in that. All right, not that.
But now though we have right most of the resources and all we have right. So are there cutting research currently being done in India?
Yes, of course. I mean, you go to depends on what field you are talking about. Like if you come to our field nowadays, you talk of metabolomics, cancer research, these things you can see. At PRC level, you can see just days before you must have seen what is prototype phosphate reaction. This is second in the world, right? And when you talk about nuclear energy, this is one field which requires knowledge of practically everything: mechanical energy, metallurgy, metals development, whatnot. And under very high radiation dose, that means when these things are operating, you have a very high radiation field, and these materials have to function under those conditions. So we are doing well. That's not a problem. I mean, quite often people ask, when will India get a Nobel Prize? This is a difficult question to answer. And I will not say that our people are not doing cutting edges. They are doing. Quite often, if you go to small places, government is giving enough funding now. So funding is not a problem. You can buy machines. Only thing is you have to have a good idea to start with. What is that you are looking answer for? All right. So the question should start there. It should not be an incremental research in something. So maybe your boss or somebody you did your postdoc with, he did something and you change from methyl to ethyl or something like that. That incremental research may not be something very new. Okay, Raman was one such case. Saha was another case. Okay. So these people, Bose yesterday, Bose was another case. So these people are there, and I'm sure many number of people are there.
Good morning, sir. Sir, what are red photons and blue photons?
I mean, you can see, if I talk of particle nature of radiation, right? So when I say I'm separating its colors, so you'll get blue light and you'll get red light. All right. Since Newton did not believe that these are rays, so he believed that there are now these photon particles and several of them. If you take now blue light, it is composed of all blue colored photons. And if you take red light, according to Newton, all right. And if you take red light, it is composed of all red colored photons. And he believed, because these wavelengths are longer, so he believed that these are bigger photons. All right. But no such thing exists. No such thing exists. This was according to his perception.
Next question. So why do these UV rays, when fall on skin, causes cancer?
See, our skin has an inherent ability. Okay, to some extent it can repair. But beyond energy, okay, either we start getting into what is called a cell damage, okay, melanin and all these things. And if it is still a higher energy, as I told you, 10 eV and onwards, it knocks out electrons. Okay, once electrons are knocked out, then you can see all sorts of mutations can start. And if the mutation starts, you know what can happen. So that's where you need to be careful once you are working. And fortunately for us, the ozone layer shields it. So nothing else comes. That is why when you go higher altitude, let's say Leh Ladakh and all that, you will see the sunlight is very piercing, very, very sharp. Okay, though it may be very cold, but you will see sunlight very piercing. Just because we are quite high, layer may be thin on a clear sky, alright, there is not so much pollution there, and directly that intensity comes in there. You got to be careful. Alright.
Thank you.
Good morning, sir. So my question is, can you explain the chambers that helped in the discovery of polonium and radium? Because like the first chamber was for ionization, and in short, how exactly these elements were discovered?
Yeah, exactly. So as I was telling on the importance of quantification, how much radiation is being emitted was the question. All right. And all the time they were saying they will take this material, wrap it in something and put close to a photographic film and only see whether the cross is developed or not, or image of something kept in between is kept or not. But this is not a fast method and it's not a quantitative method. Marie Curie wanted to have a quantitative method that I can see. And they realized that these radiations have so much energy that they can ionize the air. So if I take a radioactive, let's say take this, and it has uranium. Okay, if I put it here, the air around this will get ionized. Once it gets ionized means it forms ions and it forms electrons. If I just apply a suitable electric field, I can get some current out of this. So I will have positive ions on this side, negative ions on the current is generated. Now, how much is this current? She wanted to measure. That's where this piezoelectric crystal came into picture, piezoelectric. So when you take this piezoelectric crystal and put a weight on that, it gives rise to a positive charge. This positive charge will be used to balance the positive charge coming from this, and we will look for a null point. So once we know from a null point, then this quantity is unknown, but this quantity is known. So you know this unknown quantity is balancing this known quantity, right? So once they balance, I know that okay, it is producing these many charges. Okay. Now, if I take this, a certain amount is being produced, and I take 1 gram uranium. So according to me, let's say 1 gram uranium should give me this number. But that same 1 gram uranium with this impure element, the one which has no polonium, but they do not know there is polonium. There is something in this that is giving 10 times, 100 times, or 1,000 times. So 1 gram should give only 1 gram, isn't it? Take it as simple. I give you this a weight which is 1 gram, and I give another one which is 1 gram, but I put some lead into that. Now you will see this is not 1 gram, though it looks like 1 gram, shape is same, but it is much more, maybe 1.51. So you know there is some excess, and that excess can come from some element which is much more radioactive. So that is where the role of quantification comes. That is where the role of a fast method comes, where you know your results are quick, you can analyze quickly. All right, and this was provided by Pierre Curie's piezoelectric method.
Thank you, sir.
A very good morning, sir. Sir, my first question is, can we bend the light?
And what is that you want to do? You can bend light anywhere. No? In prism and all, you can see light is bending.
Bending curvy bend. Let's suppose here is a copy and
I mean, you know, around in this massive stars, light bends,
it bends.
of course.
We know that
Maybe what he wants to know is whether it can go in a curved path, not just
Yes, yes.
change direction.
Yeah, but that's what I'm telling you.
Yes, curve means curve that after that it again goes straight. He is slightly confused. He wants to see
But
whether I can see the back of this with the same light.
It bends around the star.
it depends on the
After
stars.
that it straightens.
That is how this back polation, though we think that the light is coming from here, no, the light was coming from this. So stars it bent around this and that's all. But you require that kind of a force, gravitational force, mass.
gravitational force can have an effect on light.
Mass basically.
And talk about
Sir, we know that light show dual nature, wave and particle, and it's still a debate. Can we say that it changes its nature by the observer, the point of view of observer?
No, it's not that way. It depends on what experiment you are doing. Simple example is our X-ray crystallography. When you are doing X-ray crystallography, what you are seeing is the wave nature of that. But you typically take copper A alpha, which is 8 point something keV. Alright. It is so much high energy that it can practically ionize everything. But what we are saying is our instrument, our detector is designed in such a way that it sees the interference pattern. It doesn't see the ionization. So it lot depends on what you are ionizing, what is how you set up your experiment. Okay. So you need to set up an experiment where you can see both simultaneously and both the effects should have same magnitude. In the sense, let us say if it is ionizing 1% and 99% is wave, you will not see that effect. So you need to have an experiment. Alright. We have done one experiment in BRC in which we see both the natures simultaneously. We see the particle nature also, we see the wave nature also. So then we were very surprised that how can it happen? And it turns out that the material has changed its form during the process. So initially the light is interacting via something called photon nature. Okay, that means you have 1, 3, 4, 5, 6, 7 photons. Its energy has to be pumped into let's say xenon gas also to ionize. So this is what we call as particle nature. Energy of 6 photons being pumped into some specific atom. But subsequently it is the wave nature which starts showing. But in the process, what has happened is you have created a system in which initially you had only xenon atoms, and now you have xenon atoms plus electrons. And if it's a nanoparticle, it's a plasma. So now the interaction is between plasma and laser or plasma and wave, and no longer between atoms. So though we see both the things together in the same experiment. In fact, these are single pulse experiments, only one pulse. Okay, let's say some 5-10 nanosecond pulse hitting a cluster. 100,000 atoms or so, and you see both the nature simultaneously. But the matter has changed its form. Alright. They are very, very predominant.
I have another question. If light shows the wave nature, let's suppose water also shows the wave nature. We can modulate the flow of water by our own choice. Can we do the same with the light?
You want to monitor the flow of light?
Yes, sir. Like the stars do.
What does that mean?
Means, let's suppose a black hole. As it bends, makes a circle like structure of light around itself. Can we do that by ourselves?
No, I think Professor Vaida will be better in position to answer this after his lecture. Okay. By most of the experiments that I have done, I take a simple laser beam which is coming out of a laser. You hit some material, you excite some material, and you go. We are not doing experiments where we are bending light, slowing it down. We don't do any such experiments. And these experiments are probably done in astronomy or other fields and all these things. We have not done any such thing. Wait till tomorrow morning. Attend his lecture tomorrow morning.
Okay, sir. Thank you, sir.
So maybe the last question now. We can interact over tea. Okay, I'll be available. Yeah, tell me.
So, like, what is the difference between Newton's theory of light as a particle and Einstein's theory of light as a particle?
If you talk about similarity, both were talking of light as wave particles. Okay, so Einstein called them. You can call them as energy packets. Okay, the corresponding German word is there. Okay, energy packets, and similarly Newton also thought like that. Okay, but Einstein's view was, even at that time, he says light is interacting with matter as a photon, but travels as a wave. Okay, if you read his paper, this very classic paper, he says it travels as a wave, but interacts with material as particles. Okay, whereas Newton did not believe in this thing. He was always telling that I cannot see the light if there is an obstacle behind, whereas I can hear the sound. Okay, which is wave. So he did not believe in that. These are similarity and dissimilarity.
And so, like, which element is more efficient for as an energy source, say for uranium, plutonium, P waves, which is more efficient and less harmful?
Efficient for what?
Energy as an energy source for something like, say, any health medical.
No. Elements are not by their own nature efficient always. Elements are giving you some sort of energy, and what we are looking at is the highest MC square value. So the greater the change in the nuclear mass, greater is the energy released. Okay, if greater is the carbon also gives you energy. You burn carbon, but what you get is hardly 2 to 3 electron volt per burning. Whereas the same thing when it comes from nucleus, a small change in the nuclear mass will give you enormous energy. Typically in this case, 200 MeV electrons, photons, right? 200 MeV neutrons, photons together. So that is what we are talking about energy. All right, and the best source will be fusion. Best source will be fusion, but we are yet to arrive there. Okay, you can take, let us say, 4 hydrogen atoms, mix them and find helium. Okay, that will be the best source, but that requires very, very stringent conditions. And though there are experiments which show for millisecond and several seconds and all this, but we are yet to have a commercial device out of that. Otherwise, as such, element-wise, you have to take care that they should not be very harmful to the people working in that industry. It should not require that to produce certain amount of energy, I have to spend much more on shielding. That is not advisable. Okay, and you should bring in sufficient delta M change in my system. That is what gives you more energy.
Thank you, sir.
Thank you so much.
Thank you, sir, for bringing this insightful history of what science and technology we are witnessing nowadays. So you can see it's an accumulation of efforts, and not only efforts, life of so many scientists, that the current lifestyle which we are enjoying, that is, the credit goes to them. And we have a lot of hopes from DAE, particularly Department of Atomic Energy. As you were saying, energy is being the main source for being a world power. You are seeing what's happening at Strait of Hormuz, how petroleum and crude oil, they are deciding the future. Many countries, like you have heard of Cuba and all, which are constrained by America under the geopolitics. So energy is the driving force, and we have a lot of hopes as India is taking stride in solar energy. I think atomic energy can as well fulfill much of our resources. So thank you, sir. With this, I will be taking a short break, and we'll be having some more enriching sessions where you will learn how we can bring about a positive change, inculcating our values of Indian cultures, because we want to be a superpower, not like America who dominates. We want to be a superpower which is always ready to help the person in need. Thank you, everyone.